thank you all for taking the time to join us. I just want to remind you that this is and everything MLPerf storage related is under embargo until the 25th at 8 a.m. Pacific. And it is my great pleasure to be here as the head of MLPerf to get to celebrate bringing together the storage working group to produce MLPerf storage version 1.0. It's been a long, fantastic journey. It has been a lot of hard work by the working group. Many of the members are in attendance here, as well as by our chairs, Curtis, who will be joining us and speaking with me, as well as Juana, Janu, and Huiho. This has been really a fantastic crew to work with. I think, as you all know, this meeting is being recorded and it will be posted to YouTube. Here are the briefing materials that everyone should have access to. If you do not, please contact Kelly at MLCommons.org. She can make sure that you have everything. She's also done a fantastic job shepherding all of these resources together. So the results are available in a Google Sheet. You should have the supplementals, which I believe are in a PDF. And then our press release, which will be going out on the morning of the 25th. And in that Google Drive, we will have a recording of this briefing, sans Q&A. Is that correct, Kelly? It's just the presentation portion, not the Q&A.
That's right. We'll have both the deck and the video of this meeting without the Q&A.
Yep, perfect. All right. So the goal here is to both celebrate what the community has done and work with our press and analyst friends to help you and the broader public really understand what does it mean to have MLPerf storage results? What do the results tell us? And help really educate the broader community of storage users, storage customers, maybe vendors that aren't represented, and the public what this means. Now, MLCommons is, in many respects, MLPerf is a competition. And we, MLCommons acts as the referee, and we provide a neutral and fair opportunity to both compete and illustrate the benefits of products, technologies, services, et cetera. And so, one of the consequences of this is, for those who are not intimately familiar with prior MLPerf briefings, we do not allow in MLCommons materials explicit or implicit comparisons. Right? So please don't ask us questions about which is faster than the other or which is better. Right, as with many things, the question of whether you should take a Ferrari or a station wagon to an event really depends on if it's soccer practice or if it's a rally car meetup. So please don't ask us questions that would pull us away from the neutral aspects of MLCommons, number one. And then number two, when members are speaking, keep in mind that this is them speaking on their behalf. The potential exception here is, of course, our esteemed working group chairs who at times are sort of likely to be speaking on behalf of MLCommons or potentially their employer. And I think Curtis here is primarily speaking as a working group chair. But if he wants to depart from that, he'll let you know. So those are sort of the ground rules. This is an agenda of what we're going to go through. Just a bit of background about MLCommons, the benchmark, the results, and then we have plenty of time for Q&A. All right. And so for those who aren't familiar with MLCommons, we are a global nonprofit, trusted, open organization that's dedicated to making AI better for everyone. We've got members on 6 out of 7 of the continents. So if you have friends in Antarctica, let me know. got over 125 members. And one of the main ways that we make ML better for everyone is through the MLPerf family of benchmarks, which is about how do we make AI and machine learning faster, more capable, and more efficient. And we've got over 56,000 results measuring compute, measuring energy efficiency, and now, of course, measuring storage. Just to step back and set a little bit of context, it's important to remember that AI and machine learning is truly an end-to-end problem. One of the things that really thrills me is that when I look at AI and machine learning, it uses all of my expertise, everything from at the lowest level, the device physics of transistors, metallization of interconnects that we use to build better silicon. And in turn, this silicon lets us build new architectures that take advantage of ML-specific optimizations. But there is not just hardware at play here. Machine learning often operates at large scale and requires extensive software optimization. In the compute side, this can be your compiler, tuning code generation. On the storage side, it can be about how you manage storage, how you do various manipulations there. It's what algorithms are you using? And in many cases, we're developing new algorithms and see them getting deployed. And lastly, it's about data, right? I started at the very bottom, but with the transistors, but when you look at some of the most powerful optimizations that we see in machine learning, many of them are intrinsically data-centric. Things like sorting the data or ensuring that data is bucketed properly. And so one of the beautiful things is that we have all of these tools at our disposal to improve performance and efficiency, but it also means that things can get very, very complicated because you can have all changes across any of these dimensions. For those who are not familiar with MLPerf and sort of our goals, this is just kind of a high-level sketch. MLPerf was started to provide fair and useful measurement for AI workloads. When we started, there really weren't standard benchmarks for the speed of training or inference or anything related to that. And that's really what MLPerf was founded to solve, is to help give us an apples-to-apples way of measuring systems performance, and which incorporates, as I said, much more than just hardware. We want to be using workloads that are representative of production use cases, not just trivial examples like MNIST. We want to have something that rewards and encourages innovation and new techniques. So, things like flash attention, which are de facto standards in AI training, was really debuted through submission to MLPerf. In order to be trusted and reproducible and valuable to both customers and vendors and researchers, we need our results to be reproducible, right? That is an underlying philosophical principle behind all of the work at MLPerf. The results need to be trusted and reproducible, and in part because that is an aspect of the scientific method that we use to drive things forward. And it should be accessible to both researchers as well as the commercial community. Part of the goal of a benchmark is to provide a guiding set of directions for the whole industry. Where do we want to be going? What are the right problems to be solving? And that's just as important for the person who's buying a storage system today as someone in academia who's looking at the novel techniques that we're going to use maybe in a product 5 to 10 years from now. And we want it to be accessible to everyone for those reasons. So the MLPerf suite of benchmarks is quite broad. I like to say, as the headline says, from microwatts to megawatts. We've seen MLPerf submissions on things from 10 or 20 microwatts all the way up to the world's largest supercomputers. And it all started back in 2018 with MLPerf training. Now, We're thrilled to have MLPerf storage here, which is broadly speaking related in some ways very closely to MLPerf training, and we'll talk about that in a couple of minutes. Over time, we've not just expanded the breadth of MLPerf to inference, to different inference platforms, to automotive and client, but we've really gone deeper as well and produced better approaches that are more consistent and reliable for measuring training. We have power measurement that we can do for inference and for training in on-premise systems and cloud systems. So you can measure power efficiency for AI training for systems in your favorite hyperscaler. So there's all of these things that we're doing to make the benchmarks, sort of deeper, in addition to going broader and expanding into new areas like MLPerf storage. And on top of that, we're tackling the ever-changing workloads. Just to share an anecdote, I think when we started MLPerf in 2018, transformers were still a very, very new technology. And no one quite had the idea of where they would really end up. So we're going to talk a little bit about the MLPerf storage benchmark. I'm going to try to get through in a couple of minutes, sort of the motivation behind it, and then we're going to turn things over to Curtis to really talk more about the details. So if you look at this era of AI and machine learning, this is, in some ways, I think, one of the most important figures to be aware of. And this is taken from a paper at Baidu Research from several years ago. And if you look, and what it's really talking about is the capabilities of an AI system as a function of the training data set size. And on the x-axis here, we've got training data set in log scale. And what it really highlights here is that at the start, when you don't have a lot of data, AI doesn't really do much better than just guessing, right? But once you get over this particular threshold, you start to see an acceleration in the accuracy of your machine learning. And that's what you see as this generalized error curve goes down. And somewhere along that curve was, one of the seminal moments in machine learning when AlexNet demonstrated that AI could beat humans at image recognition. And somewhere on that point, I sincerely hope, will be, level 5 self-driving cars so that when everyone commutes, they can read a book or talk with a friend. And so as we get more data, we are extending the capabilities and the magic of AI into new and different areas. And that's sort of oftentimes discussed as the scaling laws that were popularized by OpenAI, but they were really discovered at Baidu. And this has some profound consequences for storage because, of course, any data that we have must be both stored and accessed. And this is a much more recent presentation from Meta talking about the trends of both the capacity of storage that they need for their AI data sets and the bandwidth that they need to access that data to pull it in for training. And what you can see is that over, about 2 years, roughly speaking, the capacity has doubled, but the access bandwidth has tripled. So as we are ramping up the capabilities and pushing the frontiers on AI and machine learning, there's a real stress on the storage systems to keep up with this. And I know of examples of folks building large training clusters that had tremendous compute, but the storage really couldn't keep up and needed to be upgraded. And that really highlights the need that we have for storage in the overall workload that is AI training. So the motivation for measuring storage is much the same as with many benchmarks, right? We want to understand the storage aspects of machine learning, right? Machine learning works with data sets that are, in production so big that they just aren't going to fit in memory. And that places a tremendous burden on storage. There's oftentimes pre-processing involved. Curtis will talk about that a little bit later. But as with any benchmark, it's about how can we study the bottlenecks? How can we optimize those bottlenecks so that 5 years from now, 10 years from now, our storage systems are absolutely meeting the needs that everyone has for AI training? And then also, how can we bring buyers and sellers together so that they're making informed decisions about the storage that they pair with their compute systems, right? So those are some of the motivating factors here. So I'm going to turn it over to Curtis now to sort of talk through MLPerf storage in a little bit more detail. Curtis, you ready? Let me know when you want to flip the slides.
Certainly, thank you. So this slide is an overview of the sort of physical environment for training, and I'll go through that to set the foundation for the next slide, which will include what that benchmark actually does. So on the left there, you've got the disk and the data set, and you're going to load that into main memory in the system DRAM, right? We're not talking about the accelerator memory yet. For things like image processing, there's a fair amount of pre-processing you can do in order to effectively multiply the amount of data that you have. You can rotate, you can crop, you can change the color spectrum a little bit, and the machine learning system will treat those as mostly different pieces of data. So that's what we mean by online pre-processing. You pull it in memory, you make some changes to it, and you get double or triple the amount of data you would have otherwise. And that goes to the power law that David mentioned. So then you're going to pull out a couple of those images, if we're talking image processing, into a batch. We're going to hand that batch off to the accelerator. And the accelerator is going to do its thing, do its processing. So and something to note here is the accelerators, there's a significant investment in those. And so we need those to be kept busy. And so that's why we're going to talk about storage networking and storage, and can it keep up? You'll see us mention something called an accelerator utilization. It's about, there's a critical resource there in the accelerators. We want to make sure the storage can keep that thing fully fed with the data it needs. If you go to the next slide. So here's the benchmark, right? Same basic structure, but let's start at the left here. So because this is a benchmark that was developed within the AI community, we actually use the code that the AI community uses. TensorFlow and PyTorch are called frameworks. They are the middle layer of software between the actual application, and there's the framework, and then there is the accelerator and its software and firmware layers. So TensorFlow and PyTorch, they define how the data that in the training data set is stored. PyTorch tends to put things in one data sample per file, like if it's an image, it'd be a JPEG, or I'll just leave it at that. One image per file, and there's a lot of files, and in a nested hierarchy of folders, directories. TensorFlow generally puts many data samples per large file. So you've got a much smaller number of much larger files. And so that's an example of, we'll get into more detail, of how the framework has an impact. So we use those framework data loaders to pull data samples off of storage, and we bring them into memory. And we're not doing the data pre-processing piece yet. That's why that's not on the diagram here. That'll be one of our future things, is to pull that in, because that's actually a significant load on the storage system, the data pre-processing. We select the pieces of data that we want to build a batch from, and when we would have handed it to a hardware accelerator, we don't. We just go to sleep for the same amount of time that the accelerator would have used to crunch on that piece of data. So this benchmark, it's important to note, does not require accelerators. That makes it accessible to storage vendors and researchers, that they don't have to go out and procure a large number of these accelerators. They don't need to build them or support them or upgrade them when new one comes out. The sleep time is just a configurable variable. We run the real workloads on the real accelerators, measure that sleep time, and then we plug it into the benchmark. So we have a benchmark that leverages as much of the infrastructure as we can get from the real workloads, and then emulates or simulates the presence of the accelerators. Next slide. Okay, so significant variables. These are things that make a difference in the performance and the performance of the system overall, not just storage, but everything in the ML environment that have these variables that have an impact on the storage. So framework. We talked about PyTorch versus TensorFlow. That has an impact on how the data is encoded on storage, how much metadata needs to be processed on the way to getting the data and pulling it out, bringing it into the system that holds the accelerator. Storage networking. Is it Ethernet? Is it InfiniBand? Is it lossless? Is it RDMA? All those characteristics have an impact on keeping the accelerator busy, right? If it's a lossless network, then you don't have to wait for a timeout for packet retransmission. So that's a piece of the puzzle for us. The storage solution. So that's the solution from the vendor, how they have constructed their storage system. Different pieces of hardware, different pieces of software, how that they're all connected to each other. The type of training, single host versus distributed. Single host is, you put, for example, 8 accelerators in a white box machine. That's a very different storage workload than if you have 100 such machines with accelerators. It's not just different because it's 100 times bigger. It's different because distributed training is different. The randomization that happens in data access then gets distributed across lots of hosts, not just within one host. There's also typically there's a weight exchange in the middle, so there's a barrier where all of the hosts that are doing the training all have to come up to a barrier. They exchange weights, and then they all continue, and so that adds a different kind of stress to the storage system. Type of data: images versus text samples versus structured data, all sorts of things. I'll go into more detail about that later. Caching. The benchmark wanted to distinguish between we're going to run this benchmark code on a computer, and we don't want the DRAM in that computer to do a significant amount of caching of data, because that's not what happens in the real world. The data is generally much larger than fits in main memory, and we didn't want someone to just put 2 terabytes of memory in a node and say, oh, look at the performance we got. So caching within a node is disallowed. We actually size the data set that we're creating for the simulated data set we're creating to be larger than memory, a bunch of things. But it's worth noting that caching within the storage system is fair game, because no one's going to reboot their storage system in between runs of a benchmark or in the real world. So caching there is perfectly allowed. The architecture there may involve flash layers, maybe hard drive layers, maybe DRAM layers, all sorts of things. And so that's all fair game from the point of view of the benchmark. Next slide, please. Going on to the workloads that are simulated. So there are 3 workloads we've chosen for version 1.0, 2 of which are image processing, image segmentation, called 3D-UNet is the name of the neural network reference that we're using. There's the image classification rather than segmentation, ResNet 50. That's really important. Even though that's an older model, it's still really important for manufacturing, for example, checking the visual image of a widget coming off an assembly line as a quality check, for example. And then for something completely different, we chose a scientific cosmology workload called Cosmoflow. So there's one image segmentation is on PyTorch, so its data format, and another one's on TensorFlow, so it has a very different data format. And then the cosmology is also on TensorFlow. These workloads, we actually, when you're running a benchmark, you have to say, okay, here's the specifics we've chosen to run against. So in this case, we actually chose the NVIDIA A100 and H100 accelerators. They're representative of the latest generation of high performance accelerators. But these, and so the specific scores you'll see when you look at them are specific to these accelerators. But that doesn't mean that this is just for NVIDIA product. It's, we're actively working with the other vendors to gain their interest in also working with us and submitting. Because of the difference in frameworks and the difference in purpose, you can see the different sample sizes, for example. You have a different balance between a bandwidth versus an IOP versus a metadata workload, and we'll go into a little bit more detail of that. And compute time varies between by 2 orders of magnitude between the 3 workloads. Next slide. Right, so we are very happy to announce that we have 13 submitting organizations with over 100 results across 3 workloads. Oh, David, were you supposed to do this slide? I've forgotten.
I'm happy to do it. Yeah. This
okay,
is
please.
fine, but that's okay. Anyway, so yeah. So first of all, I want to just stress that there is a tremendous amount of work that Curtis and the whole working group did to devise this benchmark and improve it over time to be meaningful and relevant. And so, one of the measures of that is, are we getting submitters? And it's actually been really great to see the uptake in this round. As Curtis said, we've got 13 submitting organizations, over 100 results with 3 different workloads, the workloads we outlined in the prior slide. And I want to offer my congratulations, the congratulations of all the MLCommons staff to those organizations that you see up here. DDN, Hammerspace, HPE, Huawei, IEIT Systems, Juice Data, Lightbit Labs, Mango Boost, Nutanix, Simply Block, Volumes, Weka, and Yanrong Technologies. We're really thrilled to have so much participation here. And as I said, when I think about benchmarks, I think about both today and what can we do with this community over the next 5 years. So for those of you who are familiar, we have both the closed and the open division, and this is kind of a breakdown of where all of those submissions lie by logo, who's participating where. So in the closed division, as sort of the footnote says, the benchmark is very apples to apples and doesn't allow a lot of changes. So some of the things that Curtis mentioned that are fixed in the closed division are things like the data format, the ML framework, the data loader associated with that framework, number of samples per file, and batch size. And whereas in the open division, code changes are allowed, but have to be disclosed. So the within those divisions, right, closed and open, there's in this round we got both available and preview submissions. And an available submission means all of the components of the submission are available for purchase today. On the other hand, preview means that those components will be available soon. Now, what does soon mean, you might say? And it could be anything from a few days to weeks or potentially months. The key thing about preview is that it is a preview of something that will be available. And in the next submission round, anyone who submitted preview will have to submit that system into available. So I'm going to turn it back to Curtis to drive. And actually, Kelly, is it possible that I could stop sharing and turn it over to you? I have a little bit of a domestic emergency here.
I will give it my best shot. Is it possible to just leave your screen on, David?
Yeah, I certainly could.
Okay.
I just won't be able to advance the slides.
Okay. I'll get it teed up. Go ahead, Curtis, and we'll switch to deck after you move.
Sure. So key results insights. So this is all leading up to before you actually get to see the final results. So I get to opinionate a little bit here about the important things that we discovered as part of the results that were submitted this benchmark. So the explosion of the AI market is driving a wave of innovation in storage market. I mean, these 2 bullets are kind of my opinion. I have a long experience in the storage market, and so I can reasonably confidently say these things. AI and ML workloads are different than most of the workloads that are done in other spheres for the storage market. And AI is a big, very fast, high profile market. And so there's a lot of people that are pursuing it. Storage is a very stable technology. The value is stable. How important to you would a storage system be that lost data on occasion? So there's this inbuilt stability that if it ain't broke, don't fix it. But yet there's something new coming that has to be optimized for. And so those things, when something new comes along, they drive this new wave of innovation that typically doesn't happen at other times, right? Because of the focus on stability. So that's happening now. And as a storage person, I'm really excited about that there's a lot of things that are being driven into the storage products, the storage market, because of AI. You'll see that there's a broad range of storage architectures represented in submitters, from all the way down from individual device level single SSDs to enormous scale out systems. The majority of the systems present here are scale out, fully scale out. And so one of the things that's interesting about scale out is there isn't a defined maximum performance for a scale out architecture. Generally, you just add more hardware, more software, buy more gear, and you can get higher performance. So asking about max there's nuance to that question. Distributed training is very different from single node training, because generally speaking, you have a data set that is going to be accessed by 100 or 1,000 or 100,000 computers all at the same time. But that data set is your crown jewels, and you're going to be adding new data to it as you're doing your various runs. And so the storage system needs to support simultaneous access under performance constraints from some very large number of computers. That's read mostly. There'll be some checkpointing involved in that, so there's some writes to it. And then there's other new data showing up that needs to be processed and massaged and cleaned and then put into the data set. And then there's data pre-processing. So there's a lot of things going on. And so that's, especially in distributed training, there's a lot more metadata processing than there would be in a single node case. So that's adding a different axes of stress to the storage systems. As an example, the latest generation of accelerator hardware, we're using the H100 is our example of that. There was a 76% reduction in the computation time for the UNet 3D workload. So even though the data samples are big, 140 megabytes per image, that's turning into a IOP workload, a latency sensitive workload, rather than a bandwidth workload, because you've got, I think it's 3.5 milliseconds to process a batch, and you have to keep up with that. So these are, sort of soft topic. It's an attempt on our part to give you not guidance, but some insight into how to read the results. If you just say, well, what's the highest number? That's not going to give you the nuance that is telling you what's really going on with the benchmarks or the workloads or the storage solutions. So we wanted to give you some guidelines on how to view this. So it's important to note lots of work went into every result. There was lots of tuning on the part of the submitters. There was lots of questions and answers and debate about the rules for each of the various workloads. What was a fair game optimization, what wasn't. They were all trying to get the best score that they could for the particular size and structure of the storage solution they deployed. So operationally, they pick a particular make and model of storage solution, and then they run the benchmark against it, and they keep tuning the benchmark, the number and type of accelerators and the hosts running them in order to get the best score. They'll retune the storage solution as well. So when you look at it, look at submissions that are similar across dimensions. So don't compare a single SSD against a scale out solution. That's pretty obvious. But try to find something two that are only different on a particular data value. So you're only changing one thing at a time, and you'll get the closest approximation to comparable. As David said, the closed submission, the closed category of submission, sacrifices some level of flexibility and tuning in order to get a truly comparable result. Open, on the other hand, sacrifices comparability completely in order to showcase innovation. If you were to change this, look what the score you could get, where this is something that is disallowed in the closed submissions. Distributed versus single host, as I described a couple of times, is a very important distinction. The scale of the distributed solutions, how much hardware or software was applied in the storage system in order to support the workload. As I said before, scale out is a funny thing in the sense that if I put X number of dollars in, I can get a score, but if I put in 100X, I can get a higher score. And so it's the score per dollar maybe, but we don't go into dollars in this, but that kind of logic is something you should look at and think about as you're looking at the results. For different ML frameworks, different things. And just to come back to one of the core things, this is the first and open and transparent benchmark that's developed by the AI community for storage. And so we put stress on the open and transparent because it's, everyone can see what is happening and why. So that covers the listening, different things.